This is the first module on the logistic equation, right there. It is the simplest equation that is used to model population change. The two things we need are n, the total population size, which is just a total number. It's just the count of individuals, and we ignore their age, size, and other characteristics. And t is time, which here is taken to be continuous. And the logistic equation has two elements to it. The first is that we expect that population change will be linear in population when the population is small. So one way of doing this is to say that dn dt, which is the rate of change of n, equals some constant a times the population size. If there are no individuals, n is 0, dn dt is 0, and you don't go anywhere. So the idea here is that so long as this constant a is positive, the population will grow when it's small. As the population grows, you expect that there may be some regulation of population number, and this can come about, for instance, if a population is confined to some finite area, then the population spreads out over this area, and initially at least, each new individual has new space. Finally, space gets filled up, and after that, if there are resource limitations, they will produce some limitation in population growth. And when the resource limitations get sufficiently severe, or the population gets sufficiently large in relation to its resources, population growth ought to stop. So all of this kind of thinking goes into some sort of density dependence, which is expressed in a second term here, which is usually written this way. And here, this constant b is also taken to be positive, and the idea is that as n gets large, the negative term, this term is negative, will get larger, and when n gets large enough, that negative term will exceed the positive term here. So dn dt will change sign from positive, meaning population growth, to negative, meaning the population declines. Now we can ask a basic question here, which is, what is the nature of population equilibrium? And an equilibrium is simply a population size such that when the population has that size, dn dt is 0. So an equilibrium is defined by the condition dn over dt equals 0. And if we look at our logistic equation, the first thing we see that's sort of obvious is that n equal to 0 implies dn dt equals 0, which is no surprise. If there's nobody there, there's no change. And so n equal to 0 is an equilibrium for the system, and it is sometimes called the trivial equilibrium. Trivial here is a word that mathematicians use. It doesn't mean unimportant. It simply means that n is 0. Now, are there any other equilibria in the system? And the answer is yes, if the right-hand side of our equation, which is an minus bn squared, is 0, then dn dt must be 0, and we have an equilibrium. Now, this expression, it's clearly satisfied, or that condition is satisfied, equality is satisfied when n is 0, but it's also satisfied when n is equal to a over b. And you can see that when n equals a over b, the first term becomes a squared over b, and the second term is also a squared over b, and so this is indeed an equilibrium. We started out saying that a was positive and b was positive, and so this value of n is some positive number, and it is conventional to use the symbol k for it. And k is often called carrying capacity. We'll return to the implications of that in a later module. For the moment, let's focus on the term, or our equation, in which we have, if you will recall, two quantities. We have a linear term an and a quadratic term bn squared. Now, it's conventional, again, to say that this linear thing, this parameter, will be called r. And that also is simply convention. And so convention says that when the population size is small, it grows at a steady rate given by this parameter r, and it will reach an equilibrium which is given by the value k. And if we think about r and k here, then you can, instead of using a and b, you use r and k, and you can write the logistic equation in a slightly different form. And this thing in the box is kind of the standard form in which one sees the logistic. There are variations on the theme, but that's the whole idea behind the logistic model. And you can see the model originates in the idea that as population size increases, growth rate must decrease, and that it has two equilibria. One where n is 0 and there's nobody around. This can occur because of extinction, for instance, so it's an equilibrium that is of biological interest. And the other is that you have an equilibrium at some positive value of population size, and that equilibrium is conventionally called K. K stands for carrying capacity, which has to be one of the all-time great misnomers in the business, especially since it's a term that has a lot of baggage. But we'll get back to that later. So that's the end of the first module here.